Okay, good morning everyone. Sorry for the delay because of this technical issue. And tomorrow we'll be again having Dr. Sheldon sir. So I think we will be quick in all these things. But to give a brief introduction of Dr. Sheldon Williamson, he has received his Bachelor of Engineering degree in Electrical with high distinction from University of Mumbai. And to be very specific, from our college only, Father C. Rodrigues Institute of Technology. We are proud of that. And he received his Masters of Science MS in 2002 and PhD in 2006, both in electrical engineering from the Illinois Institute of Technology, Chicago. He is specializing in automotive power electronics and motor drives at the Granger Power Electronics and Motor Drives Laboratory. Currently, Dr. Williamson is a professor at the Smart Transportation, Electrification and Energy Research, that is STEER Group, within the Department of Electrical, Computer and Software Engineering at Ontario Tech University in Oshawa, Ontario, Canada. He also holds the prestigious NSERC Canada Research Chair position in Electric Energy Storage Systems for Transportation Electrification. His main research interests include advanced power electronics and motor drives for transportation electrification, electric energy storage systems, and electric propulsion. Professor Williamson is also a fellow of FDP. We welcome you, Dr. Sheldon Williamson, and it's over to you to take over the session.
Thank you. Thank you, Aqleem. So there is some disturbances coming. Hello, can you hear me clearly, everyone?
Yeah, you are clear.
Okay, there's some disturbance which was coming, audio disturbance. I don't know from whose microphone it is coming. Anyway, thanks for the great introduction. As you said, I am a Father Agnel alumni, so it's for me always a pleasure to present to you as well as the faculty as well as the students. It's an honor actually. After having gone through the bachelor's degree from Father CRIT, it is the foundation was laid in college, as you know, for engineering. All my fundamentals and the upbringing, so to speak. So the childhood was spent in Father CRIT. So forgive me if you can if I take some pauses, because I'm also coming out of a medical condition which was about a month back. I was going through some serious medical conditions, but since when Kamlesh approached me and said there is the FDP for Father Agnel, so I said it was 1 month back that I was in a very serious condition and I am still recovering. It will take 4 5 months according to doctors. I said no issues, because it is my alma mater and I will definitely present. So here I am. So please forgive me if I take some pauses in between the presentation. Acha, so today, so according to the FDP on electric and hybrid electric vehicles, one of the important topics, I was asked to choose two topics. So first I chose this topic which you are seeing on battery management systems, which is a hot topic actually, because how do you manage the energy on board the vehicle? Electric vehicles have very limited range, and in order to increase the range or the calendar life of the batteries, one of the two, you need good battery management systems. So that's what I want to present. Some of the areas of research, some of the work that we are doing. So really, through this AICTE and ATAL program academy, it is really a good initiative for this development program that is being conducted. And as I said, Father Agnel being my alma mater, I could not say no. Okay, so let's continue with the presentation. First and foremost is the group. We are a large group actually at Ontario Tech University in Canada. We have 5 professors and 80 plus graduate students. We are looking actually for new graduate students, PhD students, specifically myself. Starting from September 2021, this year was a washout. 2020, I did not hire any students because of the coronavirus pandemic, COVID pandemic. Unfortunately, Most of the professors, as you can see, we didn't hire many students because we paused and there was no university. University was closed. So we are looking for September 2021 students. Funding is there. There are, good amount of funding from industry. So those of you who are interested can always approach. Feel free to approach for fall 2021 admissions. Currently at the moment between our group, we have more than 80 research students, masters and PhD. As you can see, lab space, etc. I'll introduce later. So here you can see virtual tour of our lab, some of the work that we are doing, some of our focus areas, as you can see, solar charging. We have built solar chargers for electric vehicles. Here you can see one of my students, David, working on a battery management system. We have worked on microgrids. We have a fully functional microgrid on campus with a large battery pack of 500 kilowatt hours of Panasonic. You can see my pointer on the left hand side. Here you can see one of my recently graduated students working on a matrix converter for wireless power transfer, which I will cover in my talk tomorrow actually on charging. Today I will focus on batteries. Here you see this company eCamion. We have built a fast charger. This is a 150 kilowatt charger of eCamion. It is located on campus and several other locations. The power converter topology in this is ours. And also we are focusing on drives, a lot of power electronics and drives work. And we have automotive center of excellence on campus where we can actually test, for cold condition charging, battery performance, electric vehicle performance under cold and hot temperatures. You can go up to plus 80 degrees or minus 40 degrees Celsius. And you can create a snow or rain, ice, etc., etc. So this is just a snippet of this slide gives you a summary of what we do. So first I want to cover these three individuals' work, like Pablo, Zahra, and David, as well as some other students' work in this battery management systems that we have done in the past 5 to 8 years. There's also a book on this that I have published. You can read the book. Most of their work is in the book as well as a summary. It's by Springer. I don't know, some of you may have read it or some may not have, but if you can, there is electronic version of this you can purchase from Springer's website as well, or even from Amazon to download onto your Kindle. So take a look at this book, or a good summary of whatever I'm presenting today and much more. So I would encourage you to read it. In fact, it's a good handbook if you're just having a course also on energy management for electric and hybrid electric vehicles. So the problem with lithium batteries, right? So we always talk about safety issues, and we know that it is quite unsafe in terms of overcharging or undercharging. So here you'll see on the top two pictures, animation is showing you the failures that could occur if you overcharge or undercharge, as well as if the battery is not managed properly. So here you see fire risks because their capacity fade is quite harmful to the battery, and in terms of thermal runaway, this occurs quite frequently if not managed properly. At the bottom is a time-lapse video in terms of an 18650 cell, which is a cylindrical lithium-ion cell, as you can see, being overcharged. And you can see the separation quite clearly. This is inside the material. For those of you who are into material science, mechanical engineers, stress-related or fractures, who study these things for materials, you will see that the active material, which is at the cathode, they are basically separating over time. So when they separate, the capacity to hold charge is less. That means for electrical engineers, this means the internal resistance is increasing. And when internal resistance increases, the I square R losses are increasing, which is thermal, right? So as a natural calamity, obviously, fire will occur over time. So that's why capacity fade has to be managed. We must not allow cells to lose capacity. So that's the whole business of battery management systems. So to explain this to common public is quite difficult, right? Uh, Electric vehicles are becoming popular, and I know that India, as our country, has a mandate for 2030 or 2040 to have all vehicles electric. But to explain a business case for battery management system is very, very difficult to common people or to politicians or policymakers. Uh, Capacity fade is a real thing. Lithium batteries are not good, but that is the best solution we have today. Okay, till someone can find other types of batteries, compact and energy dense. So why it occurs is this slide is very important. You see over time, so here I'm showing an animation of 4 cells charging at a constant current. You charge them in series, but because one is under capacity, there is overcharge. This overcharge, as I showed you in the previous slide, starts to get magnified over time. Okay, so it gets magnified over time and leads to the failure. As I said, due to the capacity fade, the active material is separating and the I square R losses are increasing. And once it is exponentially increased, there is no going back and fire occurs. And that is very, very, very bad. Other thing, fire is one thing, security is one thing, safety. The other thing with capacity fade is the range will reduce, obviously, because the voltage will reduce drastically. So obviously you cannot go further, right? Calendar life will reduce, lifetime of the battery, your range will reduce. You have to replace the battery faster, unfortunately. The battery obviously is the costliest item in the electric vehicle. Okay, so therefore this slide becomes very important. You have to manage this overcharge very well. Okay, you cannot allow this to happen, and this overcharge will get magnified every other month. Even once it starts, you cannot stop it. So battery management system has to do that. So please tell me if you lose my audio, okay? And the slides. Can you see the slides and hear me well?
It's going fine.
Hello? Sorry?
It's going properly.
Proper na? Okay. Now, following up from that slide, what we did is, okay, we understood the problem. So we took some of the, so this is data from our industry partner. We took their cells. We took 4 or 5 different manufacturers actually. You can name like Panasonic, Samsung, LG Chem. These are all our partners. They are willing to test their cells, and we work with them very closely. So this data comes from one of those manufacturers, and you can see on the y-axis is the number of cycles, charge discharge cycles from that cell. And on the x-axis is how much depth of discharge or the utilization percentage of the state of charge. So when we utilize 20% of the state of charge, okay, or depth of discharge is 20%, obviously the cycle life will be higher, 3000, 4000, etc. But as you use more and more of the charge or utilize more of the state of charge, like 70%, 80%, you will see that the cycle life starts to reduce because you are now using high capacity. Okay. So in reality, on an average, if you take an average of this curve, here the dotted line shows the curve fitting that we have introduced a curve fitting function and got the curve fit. You can clearly see that the average may be around 1000 cycles. You take these data points and this one's 1000 or so, but this is not good enough. You will get maybe 4 to 5 years of lifetime out of the battery. So imagine electric vehicle, you have to replace the whole battery in like 5 years or 6 years. That is unfortunate. If you want good performance, if you want mediocre or average performance, you can still increase the life of the battery pack, no doubt. But you cannot restrict the customer. So here is the business case, right? When you are starting your own business, which I think is the way to go for India to prosper in this field and create jobs. Like you and I, like engineers, we have to create our own business. Like we don't manufacture the cells, that is clear. We don't have the raw material. India, as a country, we don't have the raw material in our earth to produce cells, to produce the batteries. We are importing this, as you know now, unfortunately, we have stopped all trade with China, or we are trying to stop trade with China. So how to manufacture, what we should do? Cells are at a premium, but to manage the cells is the key. At least in terms of power electronics, we can make a mark in the world. We can be the champions in terms of battery management system manufacturing. So manufacturing of boards such as this to manage the cells is something that we can do, or chargers, those kind of fields we should look at. Create our own business so that we can hire and recruit engineers to build these products. Okay, like for example, one of the companies I started to work with closely is KPIT in Pune. KPIT, you may have heard, who work on battery management systems and chargers. They are basically looking at creating a niche in this field. In Canada, we are working with DNV Electronics. It's a leading company who makes testers. They are looking at BMS and cell testers also. So these are some of the niche businesses that I think India can take the lead. So anyway, whole idea is shifting this curve and making it flat to about 3,000 cycles, 4,000 cycles, somehow using these poor data points and shifting them up using good battery management systems. So how do we do that? Is basically, so you identify the low capacity cell. Once you identify the low capacity cell, you can share it to the high capacity cells. Okay, so you have to identify low as well as high capacity cells using the BMS, power electronic circuit board, and redistribute the charge so that you can balance the voltages of all the cells to 100%. That is the idea. So here is an animation of a BMS. So you see, balancing these cells is the job of the cell. The green one showing you the capacity, the charge. And once the full charge reaches, you are reaching the open circuit voltage. Okay, so this unbalanced cells can be balanced using a circuit board such as this. This is a power electronic circuit board. These are the cells, the green ones, which I'm showing you here. So here you can see the animation of a BMS. Okay, each cell over here is supposed to be at less than equal to 4.2 volts. Typical open circuit voltage ranges between 3.6 or 3.8 volts to 4.2 volts for lithium ion. Okay, 18650 cylindrical cells. Different configurations can go into this board. This board has circuits. So the circuits could be either resistive or capacitive if it is low power. So example in a resistive obviously is if there is open circuit voltage goes over the voltage of the other cells, then the controller will give the command to this switch to close, obviously, and this over voltage can be dissipated across this resistor bank. You can design a resistor. Resistors are very effective. In fact, in most of our devices, portable devices like laptop, cell phone, etc., you are seeing this kind of circuit now. This is a battery management system. Very clearly, you can see like over voltage can be dissipated. I square R losses occurs here. It is dissipated in the form of heat, and this voltage is reduced and equalized with all the cells. Very simple circuit, and it works, and it is very cheap to manufacture. You can start with this. I mean, a simple BMS. This is the BMS. Okay. I mean, this can be done as a simple project in like few months, or you can replace if you don't like. Okay, there is heat generated in this case. You can go with a capacitor which is sized such that it can hold the voltage, over voltage of this. So when there is over voltage here, you close the switch, controller closes this switch, this voltage is balanced across this capacitor. Very simple. Obviously, capacitor dV by dt, you have to keep on monitoring for stress failures of capacitors also. Every component has its own downside. Resistor in the form of heat, capacitor in form of voltage stress. So you have to monitor that and replace the capacitor from time to time. But this is also a BMS. So these are very low cost configurations, which we are using today in portable electronics. Okay, so I just wanted to show you an example of a BMS. When you go for high currents like electric vehicles, then you have to start looking at active solutions. These are passive solutions. The previous one which I showed you are more passive. But when you go for active solutions, you start looking at power electronics, converters, right? So some of the converters, those of you who are in the electrical engineering field will appreciate, basically flyback converter, which I showed you on the left-hand side here, or a Chuk converter, which is on the right side here. These are all bidirectional converter. Actually, this is unidirectional. This one is bidirectional converter. But very simply, you can use these as BMS systems, right? So here I'm showing you a Chuk converter, which we developed in our lab. And for one cell, as you can see, there is 2 switches and 2 inductors, and these are bidirectional currents. These arrows show you 2 directions of current, so the cells can be balanced while charging. So we reduced actually the parts from 2 inductors and 2 switches per cell investment. So here is a business case. We in fact made a business case for this BMS to one of our industry partners, and they have started to use it in fact and giving us royalty because our US patent is pending for this. You can see 1 switch and 1 inductor per cell. So we halved the cost for the BMS. So they were quite satisfied, and it is giving good calendar life. We double the calendar life. So when I say calendar life of the battery pack, we tested it on an actual battery pack, especially Samsung and LG batteries. And our manufacturers who built this BMS, our industry partners, they were very happy, saying that now the cycle life has increased by almost double, 75% to 80%. So if the batteries were lasting initially with passive balancing they were using, they were getting around total 6 years or 7 years of life. Now they can project about 10 to 12 years of life for the battery pack using such boards. So I mean, for this board, I mean, it comes down to the cost of the board, how much you are going to invest. So when you are going to a business investor saying, hey, this board I will manufacture for you, and I can give you 75% to 100% improvement in life of battery plus safety. Don't forget, not only the calendar life, charging, discharging, plus safety. Okay, fire, against fire. People are scared to buy because fires occur, and you saw the real examples. I mean, even in Tesla, in the cars of Tesla, there have been examples of fire. So you have to be very careful. So, I mean, when you give this case to them and say the board is costing, let's say, maybe 2-3% of the battery pack cost, collection of these circuit boards. If the battery pack costs, let's say, X amount of dollars, okay, and you are building this board for 0.01 or 0.02 of X added to that, they will buy it if you can give double life of battery plus safety. Why not? That is the case you have to make, and you have to prove that. So we have data that shows that. So our industry partners are actually now manufacturing these boards. It's a new reduced parts equalizer, right? So as I said, we have protected it with the patent, and that's the important thing. You also, I mean, when you come up with your new stuff, make sure you protect it. Okay, it's very important. Intellectual property is very, very important, and you should protect your ideas. So anyway, the board that we built, this board can balance 5 cells at a time in a series. We are looking to increase that also so that we can use less amount of boards. So let's say 5 cell voltage equalizer, 5 at a time, and again 5 at a time. You see? So if there are, like I said, if each one is about 3.8 volts cell, usually in traction applications like inverter and motor, the battery pack is supposed to drive the motor. So that inverter actually works at anywhere between 350 to 450 volts DC bus voltage, as you may be aware already, right? For permanent magnet synchronous or induction motor, traction voltages are usually between 300 to 400, 350 to 450 volts. So if you're looking at 3.8, 3.6, 3.8 volts, 100 cells or so approximately. I'm giving approximate number. Sometimes in this case it's 120 cells in series. You may find that you will need 20 to 25 such boards to balance 5 cells at a time. So unfortunately, customer will say, can you reduce the number of boards? I don't want to spend so much on BMS. Okay. But I mean, still it makes cost effective sense. You are balancing the cells and you are giving double lifetime for the battery pack as well as safety. So it's not so bad. But even then, to be competitive in the market, we are trying to get this to balance up to 20 cells now. In fact, we have reached a breakthrough in our lab. So some of the projects that I'm doing now, just to give you a flavor, is if you are to join as a PhD student in my group, working in BMS area would be to, do such things like power electronic converters, which can handle up to 20 cells, adjacent cells balancing, not just 5. This was the first breakthrough, but now we are near 20. And even in the future, going up to 30 or 40 cells per board. That would be something that we would be looking for with reduced parts converters. It's a good challenge to have. Most of our papers also we present in APEC or transactions on power electronics or industrial electronics. You can see some of the publications also where we detail all these methodologies of power electronics. So yeah, I mean, we have to build the prototype and test it. So this was the first cut of a prototype which balanced 5 cells, as you saw in the previous slide. This is the hardware, just the picture of the hardware. It's a microcontroller, obviously, which controls the whole logic is in the microcontroller of the balancing. Here are your switches, MOSFETs, which do the balancing, and the inductors. So one switch and one inductor per cell, as I said. These are how they are placed on the board. That is the hardware connect to the cells, which are going in series, 5 cells. And finally, the communication port to the controller for the vehicle. Okay, this is connected to the other parts of the vehicle so that they know that the BMS is operating and so on and so forth, so that they can communicate to the BMS. Very easy project. Actually, you can do this as a final year project also. I mean, this was done by one of my PhD students, but you can do it as a project even in 1 year. You get 1 year to do project, I guess. You can manufacture this. I mean, and start a business. I think you should think of those things. You know. Okay, so it starts from equivalent circuit modeling. You can build the model of the cell. The whole process of coming to that is to understand how the cell behaves. So it's great to have this board. This is the final product. The first step is the estimation. How do you estimate open circuit voltage? If you see the equivalent circuit of a cell, one battery cell, here it is very simply put. Internal resistance is there. Okay. Here is where the loss is occurring. Voltage drop. Another loss occurs in the capacitive branches. One is for charging, one is for discharging. Okay. Like if you are to see the charge discharge profile of a battery, like if I were to draw it for you, let me try and draw the current versus voltage, 0. Can you see the drawing? Can you see what I'm drawing on my screen?
No, not yet.
Sure.
We can see the screen of equalizer chaining method.
Okay, so I am on the equivalent circuit model, battery cell model.
Yeah, battery cell electrical equivalent model.
Now I have drawn this curve.
Yeah, you are drawing. Correct. Now it's visible.
So basically what it is it is three sections are there. So three sections are there where you can see region 1, region 2 and region 3. Okay. Region 1, 2 and 3 are shown here. So this internal resistance is region 2. Then this is region 1, this branch shows you the region 3. Okay, very simple. Here you can see is non-linear. Region 1 and 3 are non-linear. Therefore, they are parallel RC branches. You can see the parallel RC branches here. These two. What we are interested in is the linear portion only. The linear portion being the region 2. And region 2, that's why it's important to keep internal resistance low so that we can get maximum linear voltage. This voltage has to be a straight line. This is what is termed as, at the end of the day, after the losses, the open circuit voltage. So this open circuit, VOC, open circuit voltage, we must keep at a maximum. That means this drop from regions 1, 2 and 3 should be minimal. Okay. So our whole goal is to start from estimating this open circuit. Equivalent circuit is very fine. Okay. It is popular. This circuit actually works. I mean, there is students who worked on this. In fact, recently also one of our colleagues from my colleague actually, Rushali, she is also attending this talk. When I did my bachelor's, she was my classmate with me in Father CRIT. Some of you may or may not know her. Rushali is now a faculty in Sabu Siddiq, but her PhD is dealing with BMS also. She is also using this circuit only. Rushali, you are there? Can you hear me, Rushali? Are you attending? So anyway,
Just a minute, I will unmute her.
if she's there, then she can give her input because many may be also interested.
Rushali
This
can unmute herself.
Rushali. It's okay. Anyway, I had asked her to read this paper by Professor Chen and Mora. This paper that I'm showing you at the bottom here, I have referenced. In fact, I will give you the PDF of these files by this slides. By the way, Aqleem, so that you can distribute. Okay.
Yes. Thanks.
Yeah, I will give, but because I couldn't share this file being so high in size and animations, etc. But the PDF I can give at least. That will be handy for the audience, listeners. So, okay, so now the whole goal is to estimate the. So the problem here is this is nonlinear equation, right? To model this is a nonlinear problem. Okay, and you have to estimate open circuit voltage within a certain percentage of accuracy. Okay, so we started to do the estimation and get the results. So here is the estimated results. You can see internal resistance and open circuit voltage, which I drew for you. Okay, and here is the error. So for estimation, we use control system techniques, which you may already know, like for example, Kalman filter or extended Kalman filters. There is least square errors method. Different other techniques are there. Now there are machine learning techniques such as neural networks. We have done, work on that as well. There is a lot of work on that. I'm again looking for students in this field as well. One of my recent master student worked on machine learning techniques. advanced ML techniques for estimation. So yeah, there is a lot of work going on in this field, because the whole idea is to estimate this open circuit voltage. If you cannot estimate, then how will your BMS know what to balance or how much voltage to balance? The accuracy has to be very good, because you cannot measure. This is one cell and this is internal. Open circuit voltage is internal to the cell. It is happening in these layers: internal resistance, capacitive layer. Okay, these two capacitive layers, as I showed you in the voltage curve. So you cannot just measure this. This is inside the cell. Okay, what you see at the outside, at the terminal, anode and cathode, if you put voltmeter, is actually terminal voltage. That will give you error. That is not the correct voltage. The voltage you are trying to balance is open circuit voltage. Okay, that is this one, and that is the error. So you can see here, I mean, this is percentage error on y-axis. We use Kalman filter. You can read the book, by the way. My book gives more details on the filtering technique and estimation technique. So the error percentage gives you 0.1%, almost 0% error. I mean, as minimal as possible, as practically possible, correct? So that was something I thought I'd show you. And then the results of the actual balancing, like in the experiments. So here you can see clearly voltage and current, right? On the left-hand side is current. 5 cells at a time, it is balancing. So the current of the pink one is the cell which is unbalanced. Current is balancing and coming to the 0 of the other cells. So it meets after about half an hour, it is fully balanced. Time is not the issue here. I mean, 10 minutes, 20 minutes, 30 minutes. This is in minutes, x-axis, and 40 minutes. So around 35 minutes or so, it is balancing. That's not an issue. The idea here is to balance the cells. Faster is not the issue. How fast you balance is the C rate. If you go for very high C rate, high currents, this will become faster. But here you are using 1 C rate, which is standard rated current. At rated current, I am charging all the series cells. So they are balancing after 35 minutes, which is fine. And here you can see the voltage, corresponding voltage. It is increasing from low voltage value, increasing the voltage and balancing to the 3.8 volts of the other cells. So it's all balanced after 35 minutes. You can see all the voltages are balanced and current is also 0, which is, there is no circulating current anymore. So the transients you can see from those non-linearities, as I said, you can see the transients in current and voltage, and you can see the balancing. Finally, here you can see the balanced current and voltage. Here I'm showing you the estimation technique, the orange one, which is the mathematical model, simulation result. You see discrete time results in the orange plot, and the blue plot gives you the experimental result of the unbalanced current and the unbalanced voltage. So you see it is balanced after 35 minutes, and here also after 35 minutes. It's that curve only. It is this curve, this pink plot that I have superimposed upon the mathematical model to show that our accuracy of mathematical estimation is accurate. You see the trend? The experimental result is following closely to the mathematical result, which is showing accuracy both for current as well as voltage. Okay, fine. So again, transients, transient state and steady state where you have reached the desired outcome. So the converter we used was a Chuk converter, modified Chuk converter, as I said. Efficiency is also important, like reliability. When you go to a business investor and say, this is the cost of the battery management system, what is causing this cost? You have to replace the boards every maybe 10 years. I don't know. You said 12 years. How do you determine that number? Is from the efficiency, because the losses are occurring in the power electronic converter. So what is the main reason why we have to replace these boards? Because of the losses. and the lack of efficiency. So what is the efficiency? Here you can see it is around anywhere between 85 to 90%. And that's another area of research we are embarking on, is how to improve efficiency of the converter. Yeah. So soft switching techniques, for example, for electrical engineers. So I'm basically an electrical engineer, as I said. So I work with circuits and power electronics. So my job is to increase the efficiency of these converters, maybe go up to 95%, 95%. How do you improve that? Is by soft switching, for example, or using resonant converters and reduced parts. Also, nowadays, replacing silicon switch with high temperature, high frequency switches, such as silicon carbide, gallium nitride switches, which are available in the market. MOSFETs, those are high, those can handle high currents and high temperatures without losing much efficiency. So we can replace those parts, and this curve now can look very easily. These plots can go up to 90-95%. So the major part of the plots are here, as you can see, because 10 to 20% is the typical power transfer between two cells. Okay, it's a small. I'm talking about a very small converter or a board. 10-20 watt is basically between two cells. What you are trying to do, the converter is placed between two cells, right? So that is why the efficiency has to be measured of the converter, which is between the two cells. So increasing this is quite possible now. What we did was silicon switch, but easily we can do that, go up to 95%. Then, of course, we started to look at algorithms for charging within the battery management system. So that was about the BMS topologies. Next 20-30 minutes I want to spend on algorithm, right? Keeping the temperature of the cells under control. While doing the charging in the BMS, the converter is charging and discharging, but the problem occurs during charging. How fast can you charge while doing BMS without hampering the temperature? So Dr. Lalit Patnaik was one of the pioneers of this work. He is currently a postdoctoral, actually, he was my postdoc. He was a PhD from Indian Institute of Science. Now he is a senior research fellow at CERN lab in Switzerland. And Vinicius finished his master's recently. With me, he has got a job in industry, and he also worked on this project. And Dr. Pranit Jayasai now is in Europe, in Luxembourg, and he is working with Delphi Automotive, Delphi R&D in Luxembourg, in near Germany. But his job is basically chargers. He came from background of automotive industry in India. He worked for Mahindra Electric for I think 7-8 years before he joined my group as a PhD student. Mahindra Electric, obviously, in Bangalore. And so these three individuals came up with this CTCV algorithm. We are actually working with an industry partner now, DNV Electronics, who are implementing this in their work. So this is some of the work that went into chargers. As you can see, these are some of the chargers. Even with eCamion, we work with eCamion to build the chargers, and this algorithm is being used for their chargers as well. So here I'm showing you the C rates, increasing C rates. So 0.2, 0.5, 1C, 2C. C rate is, for those of you who may or may not know, C rate is just a charging rate, right? So if you're 1C, means you are charging in 1 hour, rated current. Like if it is a 100 amp hour battery pack, and if you want to charge the battery pack in 1 hour, the C rate for that is 100 amps, correct? So that is the 1C rate. Now, if you want to charge the same battery pack in half an hour, then obviously you will increase the current to 200. That is 2C rate, okay? 200 amps. Similarly, 300, 400, like the higher the amps, the lower the time to charge. It is obvious, like it is simple mathematics. It's not like something out of the realm. So this C rates, as you increase, one problem is you will see the capacity on the x-axis. You see capacity on this plot. The green one shows you for 2C, double the current. You keep doing this, you will reduce the number of cycles. You see the cycle life reduces. Okay, and that's a big problem. Okay, this is the CCCV charging rate which we usually use, charging profile. On the top, what I am showing you, constant current. Okay, constant current, constant voltage. Why we use this CCCV charging algorithm? Because as soon as you apply constant current to a lithium-ion cell, the voltage jumps up non-linearly. It doesn't settle at the time exactly. Okay, it doesn't settle immediately at that time. So the best way to show it is a how you say, the best way to show it is like a rubber band. You know, rubber band theory. Like if I were to show you this kind of rigid say string attached to a stone. Let's say you have a stone. This is a rubber band. Okay. Now, if you pull this, okay, if you pull this rubber band up, this ball will go up. But it is a rubber band, so it will even go down. Okay. And again, it will go up and down and up and down till it settles finally. Okay, so this process of going up and down is shown here. It is a rubber band effect. It is going up and down repeatedly. Correct? So it is going till it settles finally with a small deflection. Finally, it will settle. So the rubber band effect is shown with constant current when you apply directly a force. This is the force that you apply. Current is directly proportional to force in mechanical terms. So the voltage, which is the effect, will go up, it will go up non-linearly. Okay, from here, it is rising. Okay, this is the cell voltage. And finally, it will settle because it has reached the steady state at this point. Okay, at this point. That is the constant current, constant voltage charging algorithm that we usually use for lithium-ion cell. Can you see the drawing on the screen? Can you see the drawing on the screen?
No, that's DC fast charging system, and on that.
Yes. So I have drawn on that, basically, showing you the constant current, constant voltage algorithm. So anyway, this rubber band effect, up and down, steady state, and that is the voltage which is reached at steady state open circuit voltage. So we use CCCV, but the CCCV has problems, and I will show you. Here is the CCCV algorithm. These are some of the existing charging algorithms. Here you can see discrete time steps, multi-stage constant current charging, 4C, 1C. You can go faster charging. You can go for pulse charging, and you can go for pulse charging using square wave or sinusoidal wave till you fully charge the cell. Okay, which is these are all the popular charging algorithms that are used either in the BMS or in the fast chargers. Why we need new algorithm? Unfortunately, most of these fast charging algorithms are not adjusting for aging and temperature of the cells. aging and temperature of the cells is very, very important. Okay, and I will show you. Aging because of the calendar life, temperature because of the safety. And also because of that reason, most of these algorithms are conservative. Okay, so they do not take into consideration the cell degradation. So the key research question is, what profile ensures fastest charging time without hampering cell life? This is very important. In fact, no product out there in BMS or chargers has this implemented in them. So if you were to make a business case to build a new product, a new charger, or a new BMS, then you must include this new algorithm into that, which is very useful from a temperature standpoint. So what we did is basically, we increased the temperature to a constant temperature, which is the same temperature as that of a CCCV. But you see, we get a higher charging rate right at the beginning. So that's something that we are looking for: fast charging and same temperature rise. Okay, so ultra fast charging, same temperature rise as CCCV. You can customize your current profile for each cell, and your current profile also adjusts for cell aging. So all these properties you will get in addition to CCCV, which is the standard technique. We published this in the Transactions on Industrial Electronics paper, so you can see that also. You cannot allow a cell to go over 8 degrees Celsius. So here is the algorithm implemented in a controller. So you can see that it is a PID controller because temperature is not very fast. So slow control loop is possible. Thermal time constant is very, very slow in terms of minutes. So once you sense the temperature from the cell and feedback, your set temperature is fed to the comparator. PID controller is enough because it is a slow loop. So you don't need PI or P controller. PID is more than enough for us with differentiator. That PID control command should go to a summation loop, a summation point. In that summer, you are putting the feed forward term, which is the charging algorithm. Whatever the fast, like 5C, 6C, whatever it may be, is added to the error of the output of the PID controller. Okay, that is summed up and given to the charger. Now the charger is seeing charging algorithm plus the PID command. Okay, very simple. So it is the charging current, ICH. Okay, very simple charger, which is given to the cell to charge. Finally, again, we are monitoring the temperature using the sensor, and the loop is closed loop. Nobody did the closed loop before, actually. It was never done before. And it's for the first time that the world got to see. In fact, when we published this paper, already the citations of this paper are close to, like, this is 2019 paper last year. Okay, within a year we got almost nearly 100 citations. So here are some results of simulation for voltage, current, and temperature. You can see the red one. The red one is the current, black one is the temperature, and blue one is the voltage. Okay, here again we use temperature model, electrothermal model. For those who are in the mechanical field, can look at this as a research field. Thermal models of cells is something that is also, we are working with our students in electrothermal modeling. Like, this is second order model, right? Very simple second order model. You may have seen already in your fundamental, energy storage. If you look at this paper, for example, by this French author Forget, 2010 paper, it's 10 years back, in fact. Second order model was derived, okay? Starting from ambient temperature, and as I said, the two capacitive surfaces, and finally the loss. So loss is fed as a current source, and then the RC parallel circuits, finally you get to the ambient surface temperature, okay? So you work backwards, you get a second order model, thermal model. This, in fact, now we have increased to a 10-layer model in our lab, more detailed, from internal core temperature all the way up to the surface temperature. Okay, it's very important because can estimate the surface temperature accurately without having to put sensor. So here you can see in the block diagram, temperature sensor is there. But if you were to estimate the cell temperature, then you don't need even sensor. The whole circuit will become cheaper to manufacture. Sensorless technique. So that is another thing. Estimation of the temperature using machine learning or using machine learning and equivalent circuit models together. That's itself a good PhD topic. Again, as I said, working with our industry partners, we have some funding for that, so that our students coming in, like I said, I'm looking for students from fall semester. We are looking for these students to work on these topics. And equivalent circuit electrical model you already know, so I'm not going to go in details. So here is the experimental setup of each part. As I said, for this study, we use the Samsung cell 18650. Okay. This is the complete setup with the temperature sensor. You can see here. And finally, the programmable power supply, the scope, and of course, the computer to host. So the battery specifications are shown here. It's a Samsung cell, I told you, 18650. Capacity is 2.3 amp hours. Very simple. Here is a charge-discharge setup. We have one of these reactor Carnegie from a company called Carnegie. Reactor balanced charge-discharger. The cell goes in and you can run the charge-discharge, whatever current you want. So up to 20 amps discharge current you can actually do. Okay. So we use that to compare all the charging techniques, which I showed you before. So for the CTCV versus CCCV, we started to compare with the most popular. So the blue one shows you the CCCV. As you can see here, CC is showing 2.3 amps. And then we did 2C charging rate with our technique, constant temperature technique, constant temperature, constant voltage. So you can see you can get higher rate of charging. The current can go up to 4.6 volts. 2C means 2.3 times 2. That is 4.6. So from 4.6 we started and reduced and came back to CCCV mode. Okay, so you can see here the time. Time in minutes is faster compared to the blue one. And most important thing is temperature rise is 7.5 degrees Celsius, equal to the CCCV. This is temperature. So we are not increasing temperature and at the same time getting faster charging. So here you see 20%, the last plot here shows you 20% reduction in charging time. Okay. And we get the equivalent voltage. Voltage is balanced. I mean, we get 4.2 volts. Correct. So, I mean, all four plots basically show fast charging, equal temperature, and equal voltage as CCCV, which is fantastic. Without increasing temperature, you're getting faster charging. Nobody showed this ever before. This is just the data from that plot only, so I'm skipping this table. I'll provide the slides to you so you can see that. Another test we did was increasing the current of the CCCV part. So by 25% we increased the rated current in the CCCV. We kept CTCV, which is our algorithm, at 4.6 amps only, that is 2C rate. But what we noticed was when we increased the CCCV current by 25%, you got a jump of 2 degrees in temperature. You see the blue one? From 7.5, it jumped to 9.4, which is almost 2 degrees Celsius, which is now going over the limit of 8 degrees Celsius. As I said, the manufacturer's data sheet says you cannot go over 8 degrees Celsius, after which capacity fade starts to exponentially increase. So active material will start to separate, and over time it will fail. So now this degree Celsius, 2 degrees Celsius jump in a cell means you're drastically going to increase the module or the pack temperature when they are packed together, the cells. Okay, and that will in fact even be more enhanced, the temperature rise when it is in a pack. This is only for a cell. Can you imagine? So you nearly need, So in our case, it is still held at 7.5, whereas when you increase this by 2.25, which is 25%, you're getting a 2-degree rise. Yes, with a 25% increase, you will get equal charging rate as our algorithm, no doubt. But the temperature rise is a big constraint, which is 2 degrees Celsius increase in delta T. So we cannot use CCCV over the rated current. And that is a problem. For fast charging, you need to go to up to 5C, 8C, 10C. Nowadays, even Tesla supercharger, they are using CCCV mode of operation. So when they use CCCV mode of operation, you can imagine the temperature rise. Okay, supercharger is like 250 kilowatts. Okay, 400 kilowatts charger. That means you're going up to 5C, 6C, and those currents will cause temperature rise above 12, 13, 15 degrees Celsius, which is way above 8 degrees allowed. Double the temperature rise. But you are not seeing that as a customer. Customer is only seeing, wow, I am fast charging my cell. What you are doing to the cell? You are reducing its lifetime by half or even more faster. 75% maybe even. You will get only 25% of the lifetime. So it's very dangerous because of this temperature rise and capacity fade. Of course, to reduce the temperature while charging, you can use cooling methods, okay, which go into the thermal management system. Cooling methods are liquid cooled, air cooled, ambient temperature cooled, so on and so forth. So you have forced air, natural convection, and insulated. So poor cooling, average cooling, good cooling. We tested our algorithm for all three. So you can see that obviously if it is well cooled, blue one, good cooling, will have less faster charging rate compared to the black one, which is poorly cooled. So that's something that we are looking at. We use some machine learning techniques, as I said, KNN method, NN neural network method, K nearest neighbor method, to estimate the temperature and use equivalent circuit models, thermal models. And this error is of 1.4 degrees Celsius in estimation of the surface temperature. So going sensorless, right? Sensorless. But this is a big error. Right now, we are still working on it because, I mean, if you're looking at delta T of 7 degrees Celsius, 7.5, 1.5 is a big number. So the error is still large. Here you can see the results actually. The temperature estimated, the blue plot, versus the dotted one, which is the, how you say, the measured, actual measured temperature from the sensor. So we want to replace the sensor. So the cost will reduce, right? So the cost will reduce if you go sensorless, vastly reduce. In fact, so really modeling becomes very important. Estimation using higher order models, as well as using machine learning techniques to estimate the temperature. So here is some of the results we compared with the other charging algorithms, and we showed that most of the data that is tabulated here is basically shown in these results here, these two plots. So that's basically enumerated here. And as I said, it's in the paper as well. So we started to create our own test system. As I said, we are working with a company called DNV Electronics. This is something we will look at closely, called the battery automated test system. Okay, this is the battery under test. We created our own test system for them. They are a company that makes testers. So these are some of the components that go in and around. This is the temperature sensor LM335 from Texas Instruments. As I said, Vinicius did this as part of his masters. You can see the cell tester in the inside the temperature chamber, and you can see the temperature chamber can range between anywhere between minus 40 degrees Celsius to 125 degrees Celsius. The chamber also has a Modbus communication system, which interfaces with the rest of the controllers and communicates with the outside environment. So you can connect or monitor this from a computer from the outside and control the commands. This is the outside view of the chamber. So I mean, this was of course acquired from some funding we received from the government of Canada for instrumentation. So you can see the cell under test over here. This circuit we showed you earlier. So again, experimental results and most of the analysis went into this paper, which we presented in Argentina just this year, earlier this year, at ICIT conference. This is the thermistor assembly. Some questions we got about this is also how do we make sure that the temperature is consistent or homogeneous? Like if we place the sensor here or here in the middle or at the end, is it going to be all the same across the cell? And the answer is no, obviously not. This is only an estimation, correct? So that's why in the feedback, it will take care of it. But if you go sensorless, then you need to estimate the temperature accurately. That's why higher order thermal modeling is very important. So that's a summary of all the results. I'm not going to go into details. I already explained this to you. Other projects which we are working on now, Yashwant also just finished his master's. He worked on supercapacitor bank switching, replacing batteries completely in hybrid storage units. So again, power and energy management, a parallel series parallel branch of supercapacitors can act as a battery, switched branch, which can use energy and also a supercapacitor bank as power. So there's no switching here, which is conventional for an ultra capacitor. So you can reduce the number of converters here in order to do that. So this is very good prospect for future of mass transit. And this is Apurva Kelkar. I think Apurva worked for some time at Father Agnel as an intern, as like he worked on some specific projects as a project intern at Father Agnel's. Although I think he did his bachelor's in I think Somaya or one of the other colleges, and he joined my group. He's about to finish. We got a project from a Nova Bus, which is mass transit bus company, and they wanted to charge and discharge their batteries, but they wanted to do it on the bus itself, 20C rate, very high discharge rate. Now that couldn't be possibly done on the bus because they will kill their batteries. So we developed a tester for them, charge discharge tester. Okay, so that was a Apurva's work, replacing that with the supercapacitor so that the battery can be dumped into the supercap. We are working on a project called APMA, which is Automotive Parts Manufacturers Association, to build Canada's first electric car. So Ontario Tech is partnered with McMaster University and Waterloo. And I am the lead from Ontario Tech to work on the energy storage part. We are also into formula racing. So most of our work, see, this is in-house built BMS for the race car. On the right-hand side, you can see, left-hand side, you can see the car itself. This is the open chassis. This is the car. Version 1 of the car. This is version 2. This is the BMS, our own battery pack that we built in-house, which is going into the vehicle. We can test for, as I said, cold temperatures and dynamometer testing with race cars, etc., or commercial cars under any condition. Right? You can actually program the drive cycle and actually run the test in ACE, Automotive Center of Excellence. Recently, Prime Minister of Canada also was at our facility to announce our bus project, as I said, that we are working on, and we are looking at electrification of buses using supercaps, batteries, and all-weather testing. So, I mean, there was funding from federal government. You can see Minister of Science also here sitting in the foreground. Minister of Science and Technology and Prime Minister of Canada, the right most honorable Justin Trudeau. who was there to present the funding. The microgrid is fully functional. You can see pictures of microgrid here. On-campus microgrid. Again, in Canada, this was the first microgrid on a campus, university campus. This is basically a $7.5 million project, which is a living lab, right? So students can actually get real data from the solar installation or from the 500 kilowatt hour battery pack installation, and then the control for the microgrid as well. So here our partners are Panasonic, GE, Hydro One, which is a utility company, power company at the state level, that is Ontario, provincial level. And also we have local utility, Oshawa, our city utility, and then the ministry, provincial ministry, Ontario, Ministry of Energy, who funded the project. So all of them, of course, industry also put cash. Professor Sood and Professor Sidhu, who are microgrid and smart grid experts, are the leaders of this project. I am a partner in this project, but my job is only to build the power converters for the charging and discharging of electric vehicles, and we are also using solar panel to charge. Tomorrow's talk will cover most of those topics. Here's another view of the distribution units, the transformers, so that we can connect to the grid, along with circuit breakers and isolators. And this is another view from the PV panels, which is housed on the Clean Energy Research Lab. This building is the Clean Energy Research Lab. I don't know if I showed you here. Yeah, this building, this one. Okay. This building on which the solar panels are installed is the Clean Energy Research Lab, CERL. Okay. Here is the building view, Clean Energy Research Lab. On top of that, the panels are there, and that is the Panasonic battery pack. This is the SCADA, single line diagram. We are on the SCADA system for the Oshawa PUC networks. They are the utility, local utility. So they shared this with us. We are here at the bottom of their network. You can see the microgrid is connected to the main grid. So whenever it is in fully operational stage, the battery packs as well as the solar panels, there you can see the numbers. Okay, so we can monitor that at all times. So with that, I will end the talk. This is the end of the slide, basically showing our research group work. Today, I covered only this middle part, energy storage, some of the last 5 years work, BMS, and I didn't talk much about supercaps and more battery work, but mostly focused on BMS. Tomorrow's talk will talk about the charger system. Okay, charging and grid interface, charging of battery packs, so power electronics, charging algorithms, topologies, wireless charging, all those sort of things. Tomorrow's talk will be covered. So with that, I will end today's talk. I thank you all for listening. So now if you have some questions, so the thing is, I have to leave as soon as possible. It went over time. I have a doctor's appointment, unfortunately, which I postponed. I have called my doctor because the talk went over today. We were delayed by technical difficulties. But I am free to take maybe few questions at this point, or you could save your questions and ask tomorrow also. It's either way is fine. Or email.
Yeah, actually, I would suggest if we can keep the question answer for tomorrow, it will be better. But still, somebody
can email also.
Yeah.
You can email me. You have my email address. Several of you have also connected with me on LinkedIn. You can message me, inbox me on LinkedIn. I am usually very fast to reply. Within an hour or so, or sometimes in minutes. I try to answer as soon as possible. So if you have any question now, for 5 minutes, I am available. I have postponed my doctor's appointment to 12:30. As I said, my doctor needs to medically monitor me at all times because my recovery time frame is 4 or 5 months actually. It has been a very serious medical issue, unfortunately, but I am recovering. So with the prayers and wishes of all friends such as you. So go ahead. Any questions?
Yes, first of all, we wish that you get well soon and recover quickly. That
Thank
is
you so
our
much.
first prayer for you all on behalf of, I think, all the members. They would be there
Thank
with
you.
me. And
Thank you.
at the same time, I would just put a suggestion. Okay, we'll keep the question answer for tomorrow because the next session is immediately lined up at 12 o'clock. And the
Oh,
speaker is available for the next team.
okay.
Yeah.
Okay.
So I hope you won't mind if we take the questions tomorrow.
Perfectly fine. Perfectly.
Yeah.
Thank you all. Thank you all. And thanks. I mean, unfortunately, this connectivity issues, but we have sorted it out. Tomorrow we will start earlier to connect before
Yes, sure. Yeah.
half an hour before. I think it should be fine now. But
Should be
still,
fine
we will.
now. Yeah.
Okay. Thanks a
Correct.
lot,
Correct.
everyone.
Okay,
Thank you, Aqleem.
Thank
And
you very much.
yeah, take care. See you tomorrow.
Okay. Okay. Bye.
Bye bye.
Okay.
I
Thank you,
request all the
Sheldon.
participants to fill the
Thank
feedback
you.
form. That's Rushali.
Rushali, thanks.
Yes,
Yeah,
I
yeah.
was there. I
Yeah,
was
yeah,
there.
I heard.
We'll talk tomorrow. Okay,
Tomorrow
fine.
itself. Yeah.
Yeah.
All the best. Okay,
Yeah.
Yeah, I request all the participants to fill the feedback form for this session and immediately join the next session because the speaker has arrived in that session. So it is day 3, session 2, which has already started. Okay, thank you all very much.